Hello and welcome. Today we're going to be talking about hybrid transmissions, their theory, operation, and diagnosis. The intro, of course, this information can be elaborated on. It can be a lot more complicated, but today we're just going to do the introduction, talk again about theory, operation, and some diagnosis to get you started. But a little background, traditional transmissions. Basically, you all should be pretty familiar with the traditional transmission from the earliest days of the automobile. There is a reason why we have these transmissions. We'll elaborate this, but basically it all comes down to the narrow power band of the ICE, the internal combustion engine. So for reasonable acceleration, efficiency, to power a heavy vehicle, we need leverage. And that's what gears are, right? They're just spinning levers. So our vehicles have had these transmissions so that we can change that ratio to allow the engine to run in its narrow power band of efficiency and acceleration. And the traditional transmission, basically here's a manual picture, not the most accurate picture, but it does prove a point that power comes in, you select a gear, it goes through the counter shaft and out through the output shaft, basically picking different ratios, much like you'd pick on a bicycle. So responsible for providing torque applied to the drive wheel to accelerate the vehicle from a stop and power at higher speeds that allow the engine to operate efficiently. Basically, what I was mentioning earlier is that those gears are needed. That way we don't, rev out of an engine's power band at low speeds, but allows us to get power off the line. So in the traditional torque converter on the automatic transmission, used to couple the ICE and the transmission gear train. This allows the engine to remain idling when the vehicle stopped. A little fluid coupler in there. It also multiplies torque. Okay, pretty impressive little unit. Talked about it in Rob's class. If you haven't taken transmissions, you'll learn more about it, but you can always YouTube a video on how a torque converter works. There's plenty of good info out there, but it uses basically the way the fluid couples the turbine and impeller right here and here, and gets redirected to the stator one-way clutch. It's going to multiply that torque and cause it, and actually drives the vehicle off hydraulic pressure. There is a torque converter clutch right here to lock the whole inverter up to 1-to-1 for like highway, higher speed cruising kind of stuff. And in the manual transmission, we use, of course, the clutch pressure plate, assembly here that is pictured. To basically, when you push in your clutch pedal, you're pushing this diaphragm, which is disengaging the clutch disc between the pressure plate and the flywheel. So that's the manual system, but it mechanically disconnects the ICE from the transmission when the vehicle is stopped. Basically, all these transmissions use a combination of gears, clutches, forks, valve bodies, solenoids, hydraulic pressure to control the shifting. It's basically needed to match engine RPM with road condition load, but if you look at these pictures, a ton of stuff that can go wrong as well. So very complicated gearboxes that are required. All these components can leak, break, crack, wear, you name it. Anything that doesn't work is going to make the transmission basically useless, inefficient, and can leave you stranded. So real complicated devices to basically just create these gear ratios. And now a gear ratio is basically, you'll see them written in 3-to-1 or 2-to-1, or in that some type of format with 1 being the last number. That basically is telling you the drive gear, the driver to the driven. And we always have the driven in 1 revolution. So we'll say, how many times does the drive gear have to rotate so the driven gear can finish 1 revolution? And in this example here, it's 3-to-1. We have a driver gear with 25 teeth, as you can see, rotating. It has to rotate 3 times for the driven gear to rotate once. Therefore, our ratio is a 3-to-1. In hybrids, we still utilize some of these traditional type transmissions. One is in the GM2 mode, and then the other one is the Honda IMA. We're not going to go into a whole lot of detail on these today, but in that GM2 mode, very familiar type transmission set up in here. Using planetary gear sets with these 2 electric motors, hence the 2 mode. It does, we'll go into it later. And then the Honda CVT, you have basically a constant velocity transmission using this belt, the steel belt system here. It doesn't have gears, but it's going to try and match what the engine RPM is needed for what load or road conditions that you're on. So the rest of the world, when it comes to hybrids, and this is like 90% of them out there, they kind of piggybacked off Toyota's system, which Toyota pioneered this in the 90s, which is to blend the ICE and the electric motors. They called it the power split device. So basically, power flows from the ICE to the transaxle damper, and then to the carrier, to the planetary gear, to either MG1 through the sun gear or MG2 through the ring gear. And basically, the damper links the engine to the input shaft of the transmission. It basically replaces the clutch assembly. This smooths out engine torsional oscillations using springs, much like clutch discs, but it doesn't disengage. There's no pressure plate to disengage on it like a throw-out bearing. It's just a one-piece unit as a damper to take out those vibrations. Think about the ICE. It doesn't provide power smooth through the 360 degrees. It's going to have power pulses when each cylinder actually fires on the power stroke. So in a 4-cylinder engine, it's only going to be every 180 degrees, right? So every 180 degrees, it gets a power pulse. That can be rough. Electric motors don't like that roughness, so they put in this damper to kind of, and springs in this disc to take out those torsional oscillations. Speaking of damper, here is the transaxle damper clutch right here, and it goes into a unit looks much like a flywheel with a pressure plate, but no throw-out bearing. But this is what it looks like. And here's the MG1 rotor. This is the permanent magnet. This is the PSD in the middle right here. Power split device, but it's basically a planetary gear set. And then here's MG2. And I'll link a video on how this works later, kind of an operational video to give you a better idea how this works. So in strong full hybrid transmissions, basically electric motors operate at peak horsepower and torque in a wide RPM range versus the ICE. So there's no need for multi-speed clutch arranged transmissions. Two electric machines are coupled to one planetary gear set where we're going to provide some type of blending, right? So the ICE and electric motors, they can kind of blend their power together to propel the vehicle. Here's a cutaway of a Toyota transaxle, and you can see right here that MG1, where my mouse is, that is the cutaway of that permanent magnet rotor. And then here is the stator of MG1 with that iron lamina right here to cut down eddy currents and enhance electromagnetism. Over here is MG2 and then MG2 rotor. Look at the gap, very, very small gap right there. Okay, so be very cautious if you're moving these permanent magnet rotors and use the appropriate tool, because your finger will become that thick if you try to put it in by hand and you're not careful. So be careful. Here are your bearings. There's your encoder resolver bearing. Basically this is a position sensor, and you have bearings and another position sensor right there. So we talked about that last week, the need for those position sensors. The computer needs to know where that rotor is so it knows where to put the magnetic field in the stator winding. Now these stator windings do burn up, and there's ways to test them without disassembling the transmission. I will show those later. So the premise of how this works is basically hold one, turn one terminology. So if you think back to transmissions, when you're looking at automatic transmissions and you had a planetary gear set, you have three members. You have the ring gear, the planetary carrier where the planetary gears are attached, and the sun gear. So if you hold one of those combinations and turn the other one, the third part has an output, right? So that's kind of your gear ratio. But basically, that's the gist of how Toyota uses a planetary gear set in what they call a power split device. So with electric motors holding and turning these parts, we're not stuck with just holding and turning. Now remember, in that image I showed you earlier with all those clutch pieces and bands and whatnot, all of those devices were there to basically hold one of those components on that planetary gear set so that the engine can turn the other component to get an output. Well, since electric motors aren't stuck with just holding and turning, we can rotate slowly in any direction. So it gives us more of an infinite gear ratio, and that's really what these transmissions have. They're CVT transmissions, a constant velocity transmission, but they're electronic, so they're known as eCVT, lowercase e, capitalized CVT. So basically reduced emissions, better efficiency. We're going to take a look at this operation now. Here's a planetary gear set. But again, Toyota calls it a power split system, power split device. I don't know if it's part of their copyright, trademark, I don't know, but that's what they call it. So basically blends the ICE with the two electric motors. Consists of the ring gear, planet carrier, and sun gear, right? It's just a planetary gear set. Been using these for going on 100 years. So the large MG2 electric motor is directly attached to the transaxle final drive. That's the differential assembly, and the planetary ring gear. That's the red in this image right here. Okay, so that red ring gear or annulus gear, that's what's connected to MG2. You look at this cutaway here, goes down through and into that MG2 rotor right there. Okay, the ICE, internal combustion engine, goes through the damper right here, and then there's an input shaft that goes through MG1 and the sun gear, and it comes and connects to the planet carrier with the little pinion gears right there. A small MG1 right here basically is connected that rotor to the sun gear. So between those three devices connected to the three components of that planetary gear, you get the infamous power split system from Toyota. So planetary ring gear always turns in the same direction as the drive wheels, and its speed is directly proportional to vehicle speed. So if the ring gear is not moving, the vehicle's not moving. And that may seem like, okay, whatever, but it's kind of good for diagnosis to know that if you push that vehicle and those tires and wheels are moving, then that planetary ring gear is in fact moving as well. Just something to think about when you're diagnosing. Again, called power split because it splits the torque between MG1 and MG2 in the ICE. The ratio of torque is fixed based on the teeth on these gears. The ring gear has 2.6 times the number of teeth the sun gear has. The torque split, therefore, is 72% to ring gear and 28% to sun gear. And you will never need to know that to fix it, but it's just good to know how it works. When the vehicle is stopped, all systems are inert, no motion, no power. Electrical energy is being used from the auxiliary battery. And then under light acceleration, this is basically a nomograph from Toyota to kind of show you how they kind of blend together. So if you look over here, this nomograph, this represents MG1, which is connected to the sun gear, the engine or ICE, which is connected to the planet carrier, and then over here, MG2 connected to the ring gear. This line has to be straight. And then the gap, the distance, you notice this is larger than this one. This is represented by the teeth. So we talked about that torque split that are fixed based on the teeth and gear ratio. That's the gap between these lines. So what the nomograph is going to show is if this straight line is here, it tells me the RPM, positive and negative, of these three components and in relation to each other. So if the engine right here, 0 RPMs, that ICE is off, and MG1 is negative RPM, and MG2 is positive. So this vehicle is cruising at a light acceleration and the ICE is off. And I know we're going positive and we're traveling because MG2 is in fact positive. In order to achieve that with the ICE off, MG1 has to spin backwards. So that's kind of how the nomograph works. And here's a little bit of a GIF on how, or GIF, I don't know how you all say that these days. But so we got electric mode right here. You notice the planetary gear set is not, or the planetary carrier is not turning, but the pinions are turning, idling there. But the carrier's not. The carrier's connected to the ICE, and then this ring gear is turning, so we know we're driving the vehicle. Okay, and then also the sun gear has to turn in the opposite direction. This is basically showing this mode right here on this nomograph. Okay, and then if you look right here, you got oops, I missed one. Normal mode. So here the ICE is running, the vehicle's driving the road, the electric motor's turning, and it's just kind of cruising. And then here's overdrive. So you can see that ICE is running and then the electric motor is turning backwards. That's part of that input to the planetary gear set. And then here's reverse mode. ICE is off, sun gear turns the other way, pivots these pinions on the planetary carrier, which pushes the ring gear backwards, hence our reverse mode. Now the ICE can turn on in reverse mode, but the MG1 will just have to spin much faster for it to go in reverse. So here's your construction again. You've got the damper, MG1, planetary gear sets in here, known as a power split device, and then MG2. Here's your bearing. There's a bearing. There's your elliptical kind of oblong rotor for the encoder resolver. And there's one right there as well. And inside here, these gears right here is what connects the final drive for gear-on-gear connection. So normally at this point in class, I would show this video of it in operation, but I'm going to link this video on Canvas that you can watch and go from here. Either watch it now or later, but this concludes part 1 I will see you in part 2.